Hello, welcome to Flipped. So today we are on properties of covalent compounds. Covalent compounds exist as either simple molecules, which are H2O2, like we have learned before. For example, they look like this, right? This is a H with another H. Okay, and this is a dot and cross diagram of a H2 molecule. Okay, similarly with the O2. They can also exist as a giant covalent molecules, which is something new. In the case of diamond and graphite, which we will talk about them in the next video. And covalent compounds, these two, are usually insoluble in water, but there are exceptions, which are HCl, SO2, and chlorine. Basically, these are the covalent molecules that can dissolve in water. Otherwise, most of them cannot. Because, for example, in the case of chlorine, is used in swimming pool, am I right? We use chlorine to disinfect our swimming pools. So this is the introduction for covalent compounds. Let's look at the first one, being simple covalent molecules. Basically, they are very strong covalent bonds, between atoms, but weak intermolecular forces. What do I mean? So basically, there are two kinds of forces here. Let me highlight them for you. First one being covalent bonds. Second one being IMF, weak intermolecular forces. So this one, maybe I should change color. This one, let's put it in purple. So this purple one, intermolecular forces, are all these lines here that you see, all these dotted lines that you see. Whereas, covalent bonds, as we learned, is really just the sharing of electrons. When they share electrons, they form a covalent bond. What I'm trying to say here is that there's very little amount of energy required to overcome these pink bonds very easily. Because when you melt or boil a compound, a simple molecule, you're actually just breaking all these weak IMFs. You're not breaking this strong red bond, which is covalent bond here. You're only breaking the very weak intermolecular forces. So one way to think of them is like these two, are not actual bonds. These are actually just interactions. Whereas this is an actual bond. So it's very hard to break an actual bond, but it's easy to break an interaction between different molecules. And because of this, they have weak melting point and boiling point. They usually exist as gases or liquid at room temperature. And they also do not conduct electricity, because you do not see hydrogen molecule, for example, to conduct electricity. That will be quite weird. Let's move on to next one, which is giant covalent molecules, which in your syllabus is really just diamond and graphite. So basically, they are also called covalent macromolecules. And it's really just millions of atoms bonded together in long chains, sheets, or 3D tetrahedral structure. We'll talk about this three in the next video for diamond and graphite. Basically, each carbon atom of diamond, is bonded to 4 other carbon atoms via covalent bond. So in this case, I'm using diamond as an example, but this applies for graphite as well. So what do I mean here is that, for example, let's talk about this guy. Maybe we shouldn't use red. Green color. This green atom here, you can see, is being bonded to 1, 2, 3, 4 other C atoms. So when I'm talking about boiling and melting point for giant covalent molecules, I'm talking about breaking all these very, very strong bonds. Compared to when I'm talking about melting or boiling point for simple covalent molecules, I'm talking about breaking all these very, very weak IMFs. So this is the difference between simple covalent molecules and giant covalent molecules. Because one of them, the top one, I'm breaking interactions, very easy to break. This one I'm breaking actual bonds, so it's super hard to break. And that's why they have very high melting and boiling point, because you need a lot of energy to break these strong covalent bonds between them. And they're usually solid. That's why they're usually solid at room temperature, and they're brittle. You can imagine diamond. You have never seen a liquid diamond before, right? Neither have I. Basically all diamonds are solid. They are also non-conductor in non-electrical conductor. I'm talking about diamond. But in the graphite's case is a bit special because of its special property, which we'll talk about later. So graphite is an electrical conductor, whereas diamond is not. So we'll move on to the next video, which will talk about diamond and graphite in detail.